Hello, everybody. And today we're going to talk about light, color, and the beginning of the universe. So before we can talk about light, we really need to talk about the fact that light moves in waves and what we mean by waves. So here you can see an image of a pond with a rock being thrown into it, and you can see the ripples moving away from the rock. And the important thing here is that the water that's here doesn't move out, it's just the up and down motion that moves out. So before the rock is thrown in, we have this undisturbed pool that's just completely flat. Then we throw the rock in, and it's going to be thrown in here, and it's going to cause some water to move up. And that's going to have some water next to it moving down, and then that's going to have some water next to it moving up, and so on. But the wave moves through. So this particle here, this bit of water that's at 1, is still at 1, but now it's moved down a bit. And the bit at 2 has moved up, and the bit at 3 has moved up, and the bit at 4 has moved down, and so on. So what you have is what we call a wave motion, where it is the motion of the material is moving through the material, in this case water, but the water at 1 isn't suddenly ending up at 5, it's staying here. And that's how waves work. So basically you have an up and down motion. In the case of water, it is just up and down of the water. When it comes to light, it's a little bit more complicated, and it's actually to do with electric fields and magnetic fields that I won't be getting into. But here's the important thing. We have up and down motion in energy, and that is what light is. And the up and down motion has a wavelength. The wavelength is just the distance between the ups. So I've got an up, goes all the way down and back up again. The distance between ups is called a wavelength. And the wavelength is basically the color. And we're going to get into that a little bit more today. And so light is behaving like a wave where the energy is going up and down. Now, we all know that light comes in different colors. I want to get into what those different colors are. As I said, the wavelength is basically a color thing. We're going to see how that looks. But what you can see here is I've got light being coming out of a torch. It's going through a slit. This just helps you be able to see the effect better. It hits a prism. This is a piece of glass that is triangular. And that causes the light to bend and get broken up into its different colors. So here we can see the different colors of light that are being split up by the prism. This is a kind of cartoony version, but it's a little easier to see what's going on. We call this bending of light refraction. And what's happening is the white light has all the colors mixed together, but when it hits the prism, the red light isn't bent as much as the blue light. And so what we get is that the light all gets split up into different colors. And so when we look at it on the other side of the prism, we can see the red next to the orange, next to the yellow, and so on. This is important because this is how we can then figure out what's going on with light. So when we talk about light, we usually mean visible light. Visible light means the light that we can see with our eyes. And actually, there's lots of different types of light that we also call the electromagnetic spectrum or electromagnetic radiation. So basically everything from radio waves all the way through X-rays and gamma rays, it's all different forms of light. But we can only see with our eyes the visible wavelengths. So just the colors from red through blue. There are lots of other colors. You can see here we still have different wavelengths. They're getting smaller and smaller and smaller wavelengths. And if we go the other way, we're getting longer and longer and longer wavelengths. These are all different colors. We just can't see them with our eyes. You can see here that for radio waves, that's involved with phones and other types of signals and radar. Go to slightly longer radio waves, we've got radio and TV. In the ultraviolet, that's where we're thinking about the light that gives us sunburn. X-rays goes through our skin and lets us see pictures of ourselves inside, and gamma rays are pretty dangerous. But all of these things are just light of different colors. I just want to emphasize that the visible part of the spectrum, the visible electromagnetic waves, are only a really narrow range. Here we've got lots of very high energy, short wavelength. So this is the ultraviolet, X-ray, and gamma rays. And this way we've got infrared and radio waves. But the bit that we can see with our eyes is pretty small. I'm going to concentrate on that, but everything that I'm talking about now, we can do with lots of different types of light. So let's talk about how light interacts with stuff. So here I've got a slab of stuff. It could be a slab of glass, it could be a slab of concrete, it could be whatever. And I've got some light coming towards it. And some of that light's going to bounce off. That's actually how we see things. You can see me because light is bouncing off me and then hitting the camera. But some of the light's going to go through. If it's concrete, not much. But if it's glass, most of it's going to go through. So it's passing through the material. And then when it gets to the other side, it's going to bounce off that side too. So you're going to get another reflection. And then some light's going to come out the other side. And so what we have is we can measure the light that gets reflected, we can measure the light that gets through, and then we can figure out stuff about what the light is passing through. And it's going to be different for different colors of light. And that's basically how we do astronomy. Now, when we talk about light passing through stuff, it doesn't have to be solid like glass. It can be gas like the atmosphere. When we have reflection where it's bouncing off of lots of different particles like the atoms in the atmosphere, we call it scattering. And so here what you can see is I've got light coming in, I've got blue light and I've got red light. And they're both coming in to the atmosphere from the sun, but the blue light is being reflected more. It's bouncing off the atoms in the atmosphere more than the red light. So the blue light comes from all directions because it's bouncing off all the atoms. The red light just makes it down to the ground. And that's why the sky looks blue, because the blue light is coming from all directions. But it's also why we get red sunsets. Once you get down to the sunset, the light is coming through so much atmosphere that it makes the light from the sun look redder. And we also get stars being reddened for the same reason. We can have other different things in the atmosphere. So if we've got dust particles like pollution or dust storms, we get really cool sunsets. Volcanoes give us good sunsets. They throw all sorts of ash up into the atmosphere, and then we get to see lots of nice, pretty sunsets. And then water droplets. When we have clouds, that's where there are little tiny particles of water, and they're a different size than the atoms in the atmosphere. And so how the light bounces off it and passes through it is different. And so we get clouds. So basically, by understanding how light interacts with different bits of material, we can understand all sorts of stuff about what's here on Earth and what's in space. So I want to talk about what we actually do see when we're taking the light and splitting it up into a spectrum, so a rainbow of all the different colors. So here what I've got is, this is a light bulb. It's actually an old-fashioned, what we call an incandescent light bulb, where it's basically a tiny bit of metal that is heated very hot and is glowing hot. And that's giving off light. And when we pass it through a little hole and then through the prism, and we get to see a spectrum, what we see is all the colors. This is what you kind of expect to see when you pass light through a prism, is all the different colors are represented. Now, I want to talk about this little graph here. This is wavelength. So this is just the color going from purple through blue, green, orange. Oh, no, I did that last time too. All the way to red. And then this is how bright it is. So here we can see the purple is not quite as bright as the blue, which is not quite as bright as the green. The orangey color is the brightest, and then it gets a bit fainter. So we've got most light coming in here and least light here, but we've actually got some of all the colors. So when you mix this up, it's going to look slightly yellowish, but it's going to, because it's got all the colors, it's kind of a whitish yellow. Okay, so that's what we get when we heat up a piece of metal and make it glow. Now, if we've got a cloud of gas, and you can think of this as being kind of like, you know, a fluorescent tube light that you might have in school, or a neon light. Basically what you've got is gas inside a tube, and then you give that gas energy by electricity, or in space we give it energy different ways, but that gas is then going to glow. And if we take that glow that's coming from the neon light or the gas cloud, and we split that up into different colors, we see something different. It doesn't have that complete rainbow. It's still got lots of different colors, but not all of them. There's lots missing. If we look at this graph again, remember this is brightness and this is the color. And so here you can see there's this two purple colors, but then there's no colors in here, and then there's a blue, and then there's no colors here, and then there's green, and then there's nothing, and then there's yellow, and so on. So here we should have orange, and there's no orange because there isn't any orange light. So depending on what is inside the gas cloud or the neon light, you're going to get a different collection of colors. So again, you know, here I'm showing you actually neon gives you these colors. So it's yellows and oranges and reds. So when you mix all of these up, when you look at a neon light, it should be orange. If you have something that you think is a neon light, but it's not orange, let's say it's green or pink or blue, it means the gas in there is not neon, it's something else. Here you can see sodium would give you yellow, and then helium would give you something whitish because you've got lots of different colors. But it wouldn't look anything like white light from a regular light bulb. Okay, so now what happens if we stick these two things together? So now I've got that light bulb that's giving me all the colors, like all the different colors of the rainbow all together. And now it's passing through a cloud of gas, or you're sticking your neon tube in front of it. And then we're passing it through our prism so that we can see what it looks like. And what we see is that we have, from the main light bulb, we have all the colors, but then some are missing. And the missing colors are exactly the same as the colors that we saw glowing when we were just looking at the gas cloud. So here we've got, two purples missing, a blue, some bluish greenish colors. This is what's missing. So remember that this overall shape, that's that continuous spectrum. That's the full rainbow that we got from the light bulb. And then these dips are where it gets really faint because most of the light is being absorbed. It's being absorbed by the atoms that are in this gas cloud. And so they're not letting light through. And so what we have then is what we call an absorption line spectrum. And this is actually what stars look like. You can think of it as being, I've got a star that is kind of like my light bulb here, but my star has an atmosphere, which is gas, and that gas is doing some absorbing. And so I get to see something that is basically a full spectrum with some lines missing because of what's in the atmosphere of the star. And so here we have the spectra of stars. This is the classification that's historical, why they have the letters and numbers the way they do. And what you can see here is that if we look at an A star, for instance, it's got a strong missing line color here, and a strong missing color here, and a strong missing color here. That's actually due to hydrogen. That's what those colors tell me. But if I go down to a G star, somewhere down here, there's lots of little faint lines in there, but they're not very bright. That's what the sun is like. So there are missing colors, but they're not so obvious. And so when we look at a spectrum, when we look at a rainbow or passing sunlight through a prism, we don't really notice this. You have to really spread it out to be able to see it. When we get down to stars down here, there's lots of light missing, and you can see they're in different places than the stars up here. This is actually a temperature sequence. This is how we put things on the Hertzsprung-Russell diagram. So these are the hottest stars, and these are the coolest stars. And we actually work this out by which things we can see. Now, there's one more thing that I want to talk about that relates to light, and that's called the Doppler effect. It actually works for all waves. So we're going to start with sound. So here I've got an ambulance, but it could be a fire truck or even just a car. When a car's coming towards you, you're on the side of the road and the car is coming towards down the road, and it makes this noise as it comes towards you. It says, "Nyeh," and as it goes past you, it says, "Nyeh." The change in the sound has to do with what we call the Doppler effect. What's happening is that as the thing's coming towards you, it's making the same sound from the point of view of the person inside the car, but because it's moving towards you, it squishes up the wavelength. So all of those ups and downs get closer together. And if you make sound waves get closer together, you make it higher frequency or higher pitch. So it sounds meow, like it's really high pitched. But if you're on the other side of it and it's moving away, now you're stretching out those wavelengths. So instead of being ups and downs very close together, they're now more spread out than they were. And so what that means is it's lower pitched. So that's why when it goes past you, it goes meow. Same with a siren, whether it's on an ambulance or a fire truck, it's going to sound high pitched as it's coming towards you and lower pitched as it's moving away from you. Well, light is a wave too, and so it behaves the same way. So here, if we look at this picture down here, I've got something that started out at S1. And so it had some light come out when it was at S1, and so it's that circle that's number 1. But then at S2, it had moved to S2, so that's going to give you, damn it, then it's going to give you the circle at 2. And then at S3, it's going to give you a circle of 3, and S4, the circle of 4. So basically what I've got is a light source that is moving in this direction, and it squishes up the wavelengths, just like it did with the sound. But now it changes the color. Remember, the wavelength is just the color. If you make the wavelength shorter, you squish up the wavelengths, it gets bluer. And if you stretch them out, it gets redder. So if something is moving towards you, it is blue shifted. the light is bluer than it would be otherwise. And if it's moving away from you, it is redshifted. The light is moving towards the red end of the spectrum. And so because of this, we can use this to work out how fast things are moving in space. Because if we know what color they should be, we can use the color that we see to figure out how fast they're moving. To demonstrate this, here I've got this top spectrum. So this is more or less what hydrogen looks like. I've got a blue line, a green line, and a red line. And this is what it looks like if it's not moving at all. If it's moving fast away from me, then it's going to have those colors made redder. That is to say, they get moved towards the red end of the spectrum. So this blue line has moved that way, this green line has moved that way, this red line. And so now it's a more greenish blue and a more yellowish green and a slightly darker red. If it's moving a bit faster, we're going to have those lines moved further. So this is a moderate speed. This is moving at an even faster speed. And so now our blue line is almost green, and our orange line is pretty yellow, and our red line is getting very dark red. It's moving towards as it goes the other way. So my blue line has got more indigo, my lime green line has got more green, and my red line has got more orange. And this one is moving even faster. You can see this one's moving so fast that the blue has gone to purple. So if it's blue shifted, we just mean the colors are moving in the direction of blue. And if it's red shifted, they're moving in the direction of red. Doesn't mean they turn blue or turn red. But this means that if I know that this is what my spectrum should look like up here, then, and I see it looking like this, I can look at how much the light is shifted, what the color shift is, to work out how fast it's moving. Okay, so that brings us to galaxies. So I talked about how stars have all light absorption lines where the light is passing through the atmosphere of the star. And so we've got lines that we can look at. Well, galaxies are just collections of stars. So when we look out into space, we're going to see a spectrum just like we do from stars. It's going to be different because it's made up of lots and lots of stars, but we're going to have things that we can look at and see how the colors change. So just to give you an idea of what you're looking at, this is a galaxy that we're seeing edge on, where we can see lots of dust in the midplane, but there's lots of starlight. And this is one that we're looking at top down. So that brings me to Edwin Hubble. This is from nearly 100 years ago now. And what he did was to use this method where, you know, he knows what things should look like in if they're not moving. And he's looking at the spectra of galaxies, whole galaxies. And he's got a measure of how far away they are. And all he did was to make a graph. He made a graph of how far away the galaxy is and how fast it's moving away from us. They're all moving away from us. So this recession velocity, that really just means moving away from us at a speed. And what he found was, as he started making this graph, and the red line here is just kind of showing you what would happen if you kind of took the average. It's basically the best line through all of the points. But what we're seeing is that we've got the stuff that's closest in, that's, you know, not too far away, is not moving that fast. But as you move further away from Earth, then it's moving faster. And the furthest away galaxies are moving the fastest. Well, that's pretty interesting, right? Turns out when he added more data, and just to give you an idea of how much he added, here we have, this is where that first graph would have been. And he added much more distant galaxies. So now these are, and this is in megaparsecs. A megaparsec is about 3 million light years. So these are things that are 30, 60, 100 million light years away, more than that. But we're still seeing the same thing. We're seeing that the further away a galaxy is, the faster it's moving away from us. Well, how do we explain that? Well, the easiest way to explain it is to think about it as being, here I've got these galaxies, and they're each in their own little block, right? So I've got a galaxy here and a galaxy here. If those blocks are getting bigger, then they are going to be appearing to move away from each other. The galaxies aren't getting bigger, they're staying the same size. This one's in the middle of this block, this one's on the edge of this one. But because the blocks are getting bigger, they are further apart. But not only that, but if we go from this one here to this one down here, the distance from there to there is much bigger once all of the blocks grow the same amount. So even though each block is growing the same amount, the galaxies that are the furthest from each other will appear to be much, much further apart than the galaxies that were closer together. They've all got further apart, But these ones that are further away have got much further apart. And that's how you can explain how some of these galaxies are moving. This is how you can explain how the galaxies are moving faster the further away from the Earth you get. Now, again, remember, the galaxies aren't getting bigger, only the space in between. Now, this has some interesting consequences. So here I've got my galaxies, and they're all spread apart, and they're all moving apart in different directions. But that means that they were once closer together. So if I say, okay, I know what direction they're moving in, and I know what speed they're moving at, I can say, okay, I know where they were a little while ago. So I'm going to go, oh, this is where they were a little while ago. And I can keep doing that. And I can say, let's just assume they just keep moving at the same speed outwards. That means they were always moving at the same speed back in time. So you can just take it back in time and get them closer and closer together until eventually everything is in the same spot. So the universe has been expanding for billions of years. And we can basically work out how long by figuring out how long before all of the galaxies would have been back in the same spot. So by extrapolating, that is just taking how fast they're moving outwards and moving time backwards and saying, okay, when would they have been back in the same point, same place? This is what you get. And that is the idea of the Big Bang, that we can see evidence that all of these galaxies were once in one spot. So they must have been exploded outwards, and that is the Big Bang. So let's just finish this up with a little discussion of where we got to from the Big Bang to where we are now. So the universe started basically about 14 billion years ago, and it started from nothing and exploded outwards as a Big Bang. And at that time, everything was energy. Now, at some point, a couple of seconds in, we start to have material, matter. And then by 3 minutes in, we've got some material that we would recognize, like hydrogen, helium. But then it takes stars and galaxies being formed before we make lots of heavy elements. So we go from having no matter to having some very basic matter to having all the atoms that you and me and the planets are made out of by processing material through stars. And that has taken us 14 billion years to get to. Thank you. Bye-bye.